Very good afternoon to everyone. My name is Mr. Arjunghule and I am research scholar of Jawaharlal Nehru Technology University, Hyderabad. And my guide is Dr.Prabhu sir. Basically, I am working on speech recognition performance or packet erasure network. That is my topic. And in order to enhance the performance of ASR, few of the factors which will degrade the performance of the automatic speech recognition system. So in this special paper, in this particular paper, I have not attained all the factors, but one of the factors I have studied which is related to the Doppler frequency shift. Yes sir?
What is BER?
BER stands for beat error rate, sir. Beat error rate. Convolution encoder for beat error rate analysis using Doppler frequency shift in the packet erasure network. Actually, here are few factors out of that. My concentration is on Doppler frequency shift, how it is related for the error performance. Actually, that is the topic. Now, in this my presentation, I am going to talk about in this flow, problem definition, research proposal and methodology and conclusion. That's I am going to talk about it. Now, requirement for any wireless communication system, that should be trustworthy system, that higher data rate should be transmitted, and that should be affordable cost, and that should be optimal performance. These are the key issues. And challenges for narrowband spectrum and losses in wireless network components. And in this my paper suggests the model for bit error ratio or rate analysis using Doppler frequency shift in the packet erasure network. That is the underlying factor in my paper. In this paper, proposed Rayleigh model channel which we are using, generalized model for which experimentation is carried out to conclude on the value of the Doppler frequency for bit error analysis. Now basically, problem definition, the packet erasure network, basically it is closely related to the binary erasure channel where bit sequence instead large data packets are used for transmission and reception, and channel suffers severe degradation and its performance. Some of the factors affecting the performance of includes bit error rate due to channel noise and Doppler frequency shift. Now in this my research objective, we have to identify bit error rate and word error rate on the channel. Actually that is my aim, and how to improve the accuracy and how to minimize the error. That is the objective. Here this is a Rayleigh generalized model which is available, transmitter, receptor and channel and error calculator. In this model, this is a methodology I have adopted where transmitter block at the first side and receptor block at the first side. In this transmitter block, basically there is an encoder. This is a factor related with the Doppler frequency shift. These are the two issues we have considered. And in this encoder, basically convolution encoder is the part which we have used. In this convolution encoder, again two modes of operation will be there. One is a continuous mode of operation and one is a truncated mode of operation. So for that model, these are the specifications used for this model. These are the specifications, and these are the simulated results. So in this side we will find the how Doppler frequency, let us say 9 Hz, 10 Hz. Actually, it is not mentioned here. It is a 9 Hz, 10 Hz, and so on. And for 9 Hz frequency, what is the error? And 16 Hz frequency, what is the error? And according to what is the continuous mode of operation and what is the truncated mode of operation and corresponding errors, these are the two errors we have identified in this my presentation.
Is that Doppler frequency or Doppler frequency shift?
Doppler frequency shift. Doppler frequency shift.
Delta of frequency.
Yes, it's very right. It is a delta. Doppler frequency shift, sir. Doppler frequency shift.
That's not
Doppler frequency. And this simulated result, it shows that if you look for 9 Hz of Doppler frequency, you will find that error rate is larger. Similarly, if you look for 14 Hz of Doppler frequency, your error rate is also larger. But if you look for, let us say, approximately 12 Hz of Doppler frequency, your error rate is drastically decreases. Actually, that is my work here, sir. Error rate is decreases for this particular Doppler frequency shift. And the same is scenario for truncated mode of operation and continuous mode of operation. Actually, truncated mode and continuous mode means whenever, let us say, if you are taking, let us say, some 4 bits, and if you are taking 4 bits each or frames each, that is a continuous mode, and truncated mode means some of the bits from the last frames will be preserved. That is a continuous mode of operation. And in these factors will be taken into consideration performances. The equalizer will be there, adapter filter will be there, encoder will be there. But in this paper, I have concentrated on encoder and decoder, and in future I am going to concentrate on adaptive filter as well as equalizer, so that error rate can be minimized and performance of ASR can be maximized. But as of now in this paper, I have concentrated only in the third part, which is the encoder and decoder. And this is in conclusive part, the same thing. The result, it is observed that your error rate is minimized or less as 13 Hz of Doppler frequency errors are minimized. That is a conclusion, and these are the references I have cited for this. And this is my small presentation.
References?
Yes, sir.
Reference slides. Reference slides.
So these are the references we have used, sir.
You are shifting your baseband frequency by some delta F. Why you are calling it Doppler frequency shift? I don't understand this, because Doppler effect is something else. I mean, when you have a motion between the source of the wave and the observer, then there is an apparent shift.
Yes, sir. I will explain, sir. I will take one moment.
Yes, sure.
Sir, actually, if this is my transmitter, sir, and if that is my receiver, then what is happening when I transmit some information from this place to this place, at that end I will get one direct path and I will get some indirect path or multiple path. And because of that result, fading will be there. That is, a degradation will be there. And when these different paths are arrived at its conclusion, so resultant frequency at the destination will little get shifted. Therefore, we are calling it as a Doppler shift. Because of the fading effect,
fading results due to destructive interference.
Interference.
Waves are going through two different paths. They are path different. There is an interference.
Yes, sir.
Doppler shift is somewhat different from that, from physics perspective. Anyway, you can where from this problem came it? Did you find any other approach in earlier papers? For Doppler, because your references does any kind of have that.
Yes, sir. Yes, sir. Actually, actual Doppler, what we are using, what you are indicating is, let us say one transmitter is there and one receiver is there, and when receiver is moving towards the transmitter, or transmitter is moving away from the receiver.
Yes.
Let us say my transmitter, I got your answer. When my transmitter frequency, let us say example 100 Hz, and receiver side I should get 100 Hz frequency. But if I am moving towards my transmitter, then my Doppler frequency will be plus minus, that will increase. If I am away from that, that is also changing. The same concept here used in terms of fading also. So when my basically it's a channel is a wireless channel, and where my transmitter and my receiver is also again moving. So my packet erasure channel, what I am trying to propose here, which is a wired channel or which is a wired channel, both way we can use, but here in this presentation I have considered which is a wireless channel. Wireless channel.
Wireless channel you can have fading. Wired channel
no, but in this particular paper I have considered wireless channel. Wireless channel. Therefore that word I have used Doppler. Some citations.
Somehow you are characterizing the change of frequency due to fading by using the principle of physics.
Right, sir. Very good, sir. I mean,
so what is packet erasure network?
Yes, sir.
Packet erasure network.
Packet erasure network is basically a binary network, which I have mentioned in my first slide, sir. Just I will what exactly the packet erasure network is.
Is this some special type of things, or it's just like a network?
Wait, I will tell you. Yeah. Yes, this is a packet erasure network, it's closely related to binary erasure channel where bit sequence instead large data packets are used for transmission and reception. That is a packet erasure network.
Let's suppose we have a complete frame of 1500 bytes that's going to be transferred from transmitter to receiver. That's a 1500 byte. That's a common
1500 bytes transmitter to receiver.
That's a common Ethernet frame.
Yeah.
And we are going to transfer it from one place to another.
Yeah.
And how we can perceive this thing in a large data packets are going to be not used, but only bit sequence is going to be used. I am not actually not. I'm not able to understand what actually means the bit sequence instead of
binary erasure model. How you are converting that to a bit sequence?
Bit sequence rather than a large data packet.
Binary, the packet erasure network is closely related to the binary erasure model where bit sequence instead large packets are used for transmission. So we are using bit sequence. Normally, you see, one frame. What is the size of the one frame?
1500 bytes.
No, it's 912. Some typical.
That depends on.
So instead considering these frames by frames, we are considering. Otherwise, you can take another way. Bit rate and baud rate. So both are the same thing. Bit rate and baud rate. It's a basically symbol rate or it is a bit rate. So similarly here also it is a frame rate or it is a bit sequence rate. There is no change, but it's a meaning whether it is a before the transmitter or after the transmission. So just we consider whether it is a symbol rate or whether it is a bit rate. So unit remains same. Similarly here also you are talking about the frames, one frame by frame. So instead considering one frame by frame, because if you look for the frame, in the frame what is happening, some header will be there or some connector will be there. So we can call that some overhead bits will be the part of the frame. So here I am not considering that overhead bit, because if we consider that overhead bit, our main objective is to reduce the error. So in order to reduce the error, if I transmit some overhead bits also, then my again number of bits will be more, so noisy bits will be more, so again error rate will be decreases. So and in this particular work, I have not considered that overhead bits. I have considered only data bits. So for overhead bits is a future part, sir. Yes, sir. Yes,
and why there is a drop at only at 13 hertz? What's the reason why? I mentioned it in the last slide.
Yeah.
Only at 13.
Data rate is decreases. Let us say for 11 hertz or let us say some 14 hertz.
Any specific reason why it drops at 13 not 14 or
yes, sir. I have noted your point. I have to observe it, but as of now, I don't have answer for it.
It's very typical that
Yeah, you are right. It is decreases, but why it is decreases, still I am working on it actually. So, but I appreciate your exact doubt, but I will think it in future.
That's good. You can have some analysis.
Yes, sir. Yes, sir.
So we thank the author for this nice